Hello, everyone. Welcome back to Exploring Creation with Chemistry. My name is Mr. Dan Martin, and this week it's going to get heated with Module 13 on thermodynamics. So, we're going to look at some heat stuff. This is so cool. We did a bunch of that last week, and we're really excited to do more of it this week. You can see part of my office and my lights and my glasses. So, with that, yes, sunglasses. They are not a filter. These are the real deal. You can touch them. You can feel them. They are not AI generated. They are here. So we're going to look a little bit about just more reaction stuff. And we get to do stoichiometry again. So you better fire up your engines because we're so excited to do more stoichiometry in this chapter. And balance equations and look at molecular masses. And this time we're doing it in the context of energy. So that's really exciting. We already know that reactions sometimes require energy and they sometimes produce energy. We've seen the terms on the slide before. These are not surprising. The big thing that is new here is we're formally going to introduce it and calculate it now. So we have previously learned, you have had this term, hopefully in your notes before. We've learned that reactions that off-put energy are considered to be exothermic. That means that they release energy to the environments. They feel warm as a result because, well, if something makes heat, you feel heat coming off of it. So lighting wood on fire is exothermic. Whoa. And then on the opposite ends, in the other corner, we have endothermic reactions, which are reactions that require energy, require heat. They absorb heat from the environment. That includes you. So a reaction that needs to take additional energy in to form the products because it has more numerous and more complicated bonds will feel cold because it's going to sap energy from the environment. It will sap energy from you, thus have a cooling effect. Scientists have a name for the energy that is absorbed overall or released overall. That term is the change in enthalpy. Now, change in mathematically is signified with a Greek letter. We've seen this before with delta T, change in temperature. Now we have delta H. H generically is enthalpy, which is a scientific word that just means energy, typically energy associated with a reaction. So when we look at enthalpies, we're just looking at energies of molecules. So a change in enthalpy would be comparing the energy amongst multiple things. In the context of this, we're looking at reactants versus products. So when you compare the reaction that is in the products versus the reactants, if the products require less energy to maintain their bonds, that means that there's leftover energy because if we have a high energy pile of bonding and then a low energy pile of bonding, there will be leftover excess energy. That makes sense. And then in the opposite regard, if we have a low number of low energy bonds, and then we're making a high quantity of high energy bonds, we'll have an energy deficit. So we need to go, hey, mom and dad, I really want to buy this car because I have my permits. I have $200 in my bank account. Can I please have $4,000? They would have to provide additional energy because you alone, in your own funds, in your own bonds, do not have enough to supply that. So they need to give you a fund infusion, and that's exactly what happens in an endothermic reaction. So when we compare energy before versus after, that quantity, that difference is called a change in enthalpy. Now, a really weird note on this is that when we look these up, they're sometimes presented in terms of per mole, which is really weird and it throws people off. Traditionally, we actually don't do that per mole thing at all, which feels weird. You're like, okay, so why is it written as per mole on the slide? Well, the reason for this is when we are looking at unbalanced amounts of energy and the reaction hasn't accounted for balanced coefficients, we can look at the energy that a single mole of H2O has. And what we acknowledge is, well, this reaction, when we balance it, doesn't react 1 mole. The balance coefficient says we react 6 moles. So presenting energy in terms of per mole accounts for unbalanced amounts. And then when we do stoichiometry, we use this little per mole to help us scale it up or down on the basis of like, no, we're not reacting 1 mole of H2O, we're reacting 6 mole. So the per mole is there only for calculation purposes. We provide answers for changes in enthalpy just in terms of energy units. So it could be kilojoules, it could be kcal, it could be cal, it could be joules. Name any energy unit. So with that, we are going to scroll through chat. I'm guessing there aren't really any questions at this point. Folks like the sunglasses. Amazing. Some people have joined me on camera with sunglasses. Love it, Sterling. Love it, Jerusalem. We're doing the thing. So where we're going with this, we can visually depict what change in enthalpy is with a graph. Cool. So this graph, although we haven't labeled the axis with numbers, we could make up some numbers to kind of demonstrate a point. This graph describes the total energy that is stored in the bond of all of the reactants contained in this generic reaction. And then it shows like, oh, look, the energy that was in the bonds went down. And then it shows the new amount of energy that is in the products. Okay. So if we were to pretend that there was a labeled axis, there's not. But if we were to pretend, and let's say that the y-axis for reactants said, this is 800. Yeah, we'll do 880. This is 880 kilojoules of energy. And if the products on the axis were labeled as like 220 kilojoules of energy, we could calculate how much energy change that is. That would be a change in enthalpy. And a change in enthalpy would be calculated by taking the difference of those amounts. Do you remember the order that we calculate delta T in? We do initial minus final or final minus initial? What do we think, chat? Chat wants a car. Jerusalem says initial minus final. Sarah says final minus initial. Lydia says final minus initial. It is final minus initial. So the final thing that we end with in terms of making chemicals would be the product. So if we take the product's energy and we subtract the reactant's energy, final minus initial amount, right? We'll get the change in enthalpy off of this graph. Now that is going to obviously come out to a negative number. It's not hard math. You can probably do that in your head. However, again, you don't get extra points on tests for doing mental math. So you might as well use your calculator to check the accuracy of your mental math. That comes out to negative 660. Also, it has kept the precision to the tens place like the other measurements. What does that mean? Well, it means that we lost 660 kilojoules worth of energy. Another way to say that is we had an extra amount of 660 kilojoules of energy. There's 660 kilojoules less energy in the products, which also means that 660 kilojoules of energy would be released to the environment. Exothermic reactions have negative delta H values. Now, there will be a table that demonstrates that, but that would be a key note that we need to eventually organize and take and probably maintain for reference on an eventual crib sheet for this module. All right. And you can, of course, take notes on the definition of delta. So then we want to look at the opposite effect. Obviously, this will have a positive sign because they're opposites. When we have an endothermic reaction, we have a gain of energy. There's not a lot of energy in the reactants. They have low energy bonding. The products have high energy bonding. We have to add the deficit in. We're begging our parents for a car. They're going to give us a fund infusion, hopefully. And if they don't, we won't get a car. If we don't get that extra energy, the reaction isn't going to go, right? And of course, you know that many reactions around you are not going right now. Not only is it because it might be an endothermic reaction, but this chapter we do learn about activation energy. Activation energy is the reason why the exothermic reactions of combustion are not happening around you right now. So we'll get to look at that in a little bit, but I think we can all agree that it is good that the room you're sitting in is not actively ablaze. We like that. It's good when reactions just don't happen. We don't want that to happen. I personally do not enjoy being on fire, even though I can shade the brightness from it right now. So, again, we can determine the change in enthalpy whenever we look at one of these grapharoonies. I'll make up some numbers again because the axis is unlabeled. That is not meant to be negative 250. Let's make that an arrow to make that very clear to us. If the reactants start at 250 kilojoules and they end up at, I don't know, 910 kilojoules, we can calculate how much energy was added by taking final minus initial, products minus reactants, and that will give us the change in enthalpy, the net amount of reaction. That's energy go up, energy go broom broom, the amount of energy that was added to these chemicals. Final minus initial, so the final amount this time is that 910. The initial amount that we started with was 250. Again, you are allowed to use a calculator, although the mental math here is not that much of a mental load. It's good to check your mental work. That comes out to 660, and it's positive. Now, the sign is implied, but I want to emphasize the fact that this is a positive number. No, you do not need to write a positive sign, but I want to emphasize that it is a positive sign. 660 kilojoules of additional energy would need to be added for these products to form, for you to buy your car, right? You need additional money to make it go broom broom. So our book gives us a table to summarize what the signs mean on these enthalpies. I will not give you this table on the test. This is what we call a study table that just helps you remember what the signs mean. When we have positive changes in enthalpy, delta H's, those are endothermic. We've already learned that endothermic reactions require energy to be put in. Another way to say that is absorbed. And exothermic reactions are the opposite. They have negative energies because the reactants are higher energy, more energy in the bonds. So that excess energy then gets released to the environment and they feel hot. Usually exothermic reactions are pretty dramatic. Things like lighting your house on fire, very high energy, gonna release a lot of energy into the environment. Or things like the combustion reaction in a car, right? Gonna double check chat. Make sure we're doing okay. Chat doesn't believe that I can keep my sunglasses on the whole time. Okay. Challenge accepted. When you did the experiment where you dissolved the lye in water, says Henrik, he was shocked how hot it got. Yes, it's an incredibly exothermic reaction. Hopefully, Henrik didn't die, although he did type that message, so we're pretty sure he's here with us. People are throwing banana peels behind them, enacting real life Mario Kart. All right, so people are following. Excellent. Let's go through a problem then. Unfortunately for us, chemistry in its natural state is heavily accumulative. Oh no. No, not the gumdrop buttons. We are going to have to remember the definition for complete and incomplete combustion. And by remember, I really just mean in a very heavy-handed way. Maybe put this on your crib sheet. So this problem says that this carbon and hydrogen containing molecule, which you may or may not recognize as methane, recognizing it doesn't affect your ability to do the problem. We have this fuel source. It's natural gas. Wowza. It's going to undergo complete combustion. And this problem asks us to do something stupidly simple. So before we get into the review concept, all the problem in terms of the new thing is asking us to do is to look at this given change in enthalpy, this delta H value. Recognize that this delta H is negative. Negative delta H's are exothermic. And when we have an exothermic reaction, we think of the energy as a product. So that could be an additional note that you could write on this table is exothermic reactions can be thought of as products. And endothermic reactions, the energy can be thought of as a reactant. On the example problem, that's the new thing. Exothermic energies are products. All we're going to do is we are going to include the energy in the balance reaction. Everything else is review. So in a perfect ideal world, this is a really easy problem. I fully acknowledge that you're human. You also are taking a whole section on Hamlet right now, and you really don't want to get thee to a nunnery. You're so distracted by life. I acknowledge you probably haven't memorized your chemistry textbook, so a bunch of things have fallen out of the holes that are the pasta strainers of our brain. So, we do need to remember what complete combustion is. The definition for complete combustion says that whatever fuel is named, CH4, will interact with O2 in the air. Yes, we could label phases. I'm not worried about that right now, but both of those are indeed gases. Complete combustion says that the products will be water vapor. If we were to label the phase, we would put a G in parentheses next to it. And let's do it. We'll be completionists. We will label the phases. We know these are gases. It's in the definition. And then the other product will be CO2. And then the new thing says, write that energy in the actual reaction. So I very sillily wrote too big because I need space to write this number. Because it's exothermic, it goes on the product side. That's the new thing. This problem did say to write the balance reaction, though, so we need to balance this. You don't do anything to the energy when you're balancing it. When we're given enthalpies, those enthalpies are the amount of energy produced by one instance of the balance reaction. So this is just review stuff, right? We need to make sure that we have the same number of carbon on the reactants versus the products, the same number of oxygen, etc. We'll do that. Carbon is already balanced, but hydrogen is not. So we'll put a 2 in front of H2O so that we have 4 hydrogens on the reactants and the products. We then have to deal with oxygen. On the products, we have 2 oxygens from the 2 waters, as well as 2 oxygens from the 1 CO2. So 2 plus 2 is 4. And on the reactant side, we currently have 2 oxygens. So we can make sure that we also have 4 oxygens on the reactant side by putting a 2 in front of that O2, and then we're all set. Okay, so if this reaction runs exactly as balanced, it will produce 803.1 kilojoules of energy. If we were to run this reaction as balanced twice, we would produce twice as much energy. This is ultimately why when you burn more wood, it is hotter, right? More reactant, more product, therefore more energy, because energy is a product. All right, let's go over to chat. Make sure that we're feeling okay over there. If there's any questions, you should type them in chat. Sterling says chat's feeling good. We're vibing in chat, which is excellent. We love that. I think conceptually we're feeling okay. The number of sunglasses is multiplying. I love it. All right. So if we're feeling good there, we're going to move to one of the more annoying ways to calculate a change in enthalpy. There's multiple ways to do this. Ultimately, the method that you select for choosing how much energy is present when something reacts is dependent on what information you're given. The method that we're going to start with is called bond energy. This is the most annoying way to calculate the energy associated with a reaction. because it's tedious. You have to not only draw the Lewis structures accurately for every single molecule in the reaction, but then you have to painstakingly count all of the bonds that exist. And that's really, really, really annoying. It's obnoxious. It is time consuming. I personally do not think it is hard. If you are struggling with these, you are probably not struggling with the new thing. You're probably struggling with a piece of review information, such as Lewis structures, or you just tend to have a very impatient personality, so you're not writing down as much as you should, which therefore is increasing the amount you're doing in your head, and the mental load of these problems without writing things down is extremely high. If you're not writing things down, you're going to have a really, 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 really hard time. So we want to make sure we're taking good notes. And if necessary, you are reviewing the section on Lewis structures because you will need to draw them accurately to get the correct answers to these math problems. So where the concept of bond energies come from and how we can do this is we know that in an attraction between two things, it doesn't matter if it's an attraction due to a covalent bond or if it's an ionic attraction, or even if it is the binding energy that holds an atomic nucleus together, or even the attraction between two magnets. We know that any bonds or attraction that exists throughout science and throughout the created universe, that energy is holding those things together. And it, in kind, also takes energy to separate those materials, but it also frees the energy that was stored when you do that. So that is where the energy of formation comes from, as we'll look at in a little bit. Not only are these energies that are stored, they're energies that are required to get things going. So they're both at the same time. And if we were to look at an individual water molecule, we see that 1 mole of water, ooh, that's really confusing because it's easier to think about an individual water molecule, right? We could calculate instead the number of calories in a single water. That's not what is labeled with the units on the slide, however. The problem says that 11,000 calories per mole of H to O bond, and that's really confusing language. We could determine the number of calories in a single HO bond, and when we do that, we see why we don't. So we know that a mole is 6.02 times 10 to the 23rd. So if I type in 11,000, which is the amount of energy when we have 1 mole of this bond. Okay. If I then divide that by the definition of a mole, we'll get the energy that is in a single hydrogen to oxygen bond. So if I divide that by 6 times 10 to the 23rd, I get this insanely tiny decimal. And I don't think anybody wants to write down the energy that is in a single hydrogen to oxygen bond as 1.85 times 10 to the minus 19th. That is such a tiny decimal that you don't care, right? And also, in terms of the scale that we work on when we're measuring things like water, we tend to have big samples, not individual molecules, right? Now, it is helpful to draw individual molecules because you can't depict 602 septillion water molecules on a sheet of paper. You're not going to draw that. That's annoying. So we tend to draw singular copies of the molecule even when we're talking on the scale of moles. So instead, we describe how much energy is in 602 septillion of this hydrogen to oxygen connection. If we have 1 mole of water, we have 2 moles of that bond, which sounds really ridiculous. But what we need to remember is that there is a difference between counting units and parts. If we have a single Wyatt, looking at you, Wyatt, looking dapper over there. We have a single Wyatt. He has 2 hands. Whoa. If we have clones of Wyatt, if we were to have 100 Wyatts, we would have Wyatt 100 times. Those 100 Wyatts each have 2 hands. If we were to count how many total hands we have in our sample, 100 Wyatts, 2 hands each, we would have a total of 200 hands. And the reason why I'm pointing this out is the way we count moles works the same way as counting Wyatt's hands. Because if we had a mole of Wyatts, we would have 602 septillion Wyatts. Each of those 602 septillion Wyatts has 2 hands. So we have 2 times 602 septillion. 602 septillion is just a mole. So we have 2 moles worth of hands, which sounds really weird. But when we deal with really big numbers, it gets really weird really quickly. So in the same way, if we have 100 water molecules, we have 2, each water molecule has 2 of this bond. We have 200 of that bond. Or another way of saying that, if we have 1 mole of this molecule, each of those molecules has 2 of this bond. Another way to say that is we have 2 mole of that bond. This is no different than saying if we have a bajillion Wyatts, we have 2 bajillion hands. If we have a bajillion water molecules, we have 2 of this bond. So we have 2 bajillion bonds. We have 2 moles of bond, right? The language is confusing because you're not used to talking about piles of material like this. Asher wants to know if this is the coolest class this year. I don't know. I can't commit to an answer on that because it's on the recording. It'll make the other classes sad, so I can't answer it. It's not allowed. Just double checking chat. People are joining the Sunglasses Club off camera. Love it. You're with us in spirit. All right. So where this comes in, please don't write this table down. This is the data table. The rule on data tables is I will give you data tables on the test. This will be in the instructions. So you don't need to write this on your crib sheets. What you probably do want to do, though, because you'll be doing problems like this in the textbook, is you probably want to put one of those little tabs on your book where this table is located for quick reference. Okay. So what this table tells us is effectively the amount of energy that is stored in one copy, not one copy, 1 mole of that bond. And that is a really weird number, but because we balance equations in terms of moles, it's actually not. So we talk about that the same way we talked about these water bonds. And if we know how many moles of each chemical are in a reaction, and we draw their Lewis structures, we can determine the total energy that is stored within a mole of that molecule, which is cool. So we have all of these energies for these different bonds. What I want you to notice is that the way that we calculate change in enthalpy for this particular type of for this particular method flips the definition for delta H. This is the one and only time that this will happen this year, so be very, very, very careful. It is described in terms of the energy required to break the bonds. That would be the reactant bond energies. And then we subtract the energy that is released when those bonds form, in other words, the product bonds. And it is phrased this way on purpose. It doesn't say reactants minus products, because it is inverting the relationship, because we're talking about 2 different things. We're talking about bonds that already exist and needing to put energy in to split them apart. And then we talk about energy that off-puts from the new bonds that form. Those are different. There's a mathematical proof that goes into where this equation came from and a bunch of assumptions that chemists made that our book doesn't get into. I'm not going to get into them because I do not think it is that important, although if you are a process-oriented human being, feel free to look up where this derivation came from on your own time using a search engine of your choice. What I do want to highlight is the practical aspect of applying it, which is just write this on the crib sheets, flag it maybe with a highlighter so that you don't mistakenly swap which one you subtract from which one. Energy required to break bonds would be reactant info. Energy required released when bonds form would be product info. And again, the reason for this is we're talking about 2 different things. It ends up inverting the relationship when we analyze it mathematically. We'll just accept it. All right, chat. I'm getting peer pressure in chat to say that they're the best section. Okay. So we're going to practice with this. We're going to look at the reaction that we already did some math on. We have the combustion of CH4. When we're given reactions to do these problems, we do need to make sure that it is balanced. We balanced this previously. We know how it should be balanced. It is indeed balanced, folks. So it is good to go. To do these problems, we need to draw the Lewis structure of every single one of these molecules. Now, you're probably a little bit rusty in this regard, so we'll remember how we do this. We do need the periodic table for drawing Lewis structures. It's been a while since we've pulled out the glorious periodic table as we see it here. So what we're interested in when drawing Lewis structures is the valence electron count. We recall that when we're in an A column, in other words, we're not dealing with one of these awkward ducklings of metals, the column number tells us the number of valence electrons. Look at carbon in all of its glory. Our first molecule has a carbon and a hydrogen. Carbon has 4 valence electrons. Our little leftist, hydrogen, has 1 valence electron. So we have 4 valence electrons from 1 carbon. Every instance of hydrogen in our molecule will have 1 valence electron. We have 4 of those. So the valence electron total that we have for CH4 is 4 from carbon. And then we have 1 from hydrogen, but we have 4 copies of hydrogen in CH4. So therefore, the total valence electron count that we have to draw the Lewis structure is 8. Okay. We then pick the central atom that is we're going to build the entire structure off of. The rule on that is to pick the atom that is furthest left that is not hydrogen. So it's obviously carbon, but the conceptual reason that we learned about for that rule in the module that covered Lewis structures was that as we go left on the nonmetals, the number of valence electrons that atom has decreases. Therefore, the number of positions of sharing that it has, number of times it's capable of sharing, goes up. And the atom that can make the most bonds has fewer valence electrons because it has more positions of sharing. This is why carbon is kind of one of the best atoms. One might say it's goated. It's one of the greatest of all time atoms for building structures because it has 4 valence electrons. It has 4 positions of sharing. It can make a lot of bonds. This is why your proteins and amino acids and DNA are carbon-based. So really, really good scaffolding of an atom. Long story short, for practical use here, carbon is going to go in the middle. And we'll attach all of the hydrogens to it. We will then subtract the number of valence electrons. And let me actually bump this picture over because I'm encroaching on the land of subtraction. We'll draw it off to the side instead. We're going to attach all those hydrogens onto the carbon. There's 4 of them. And the first thing we learned about drawing these bonds is that we subtract 2 valence electrons for each stick, each bond that we drew. We drew 4 of them, so we'll subtract 8, which reduces our valence electron budget down to 0. We then check for stability. Every single atom needs to have its stable number in the structure that we drew. Hydrogen is stable at 2. Each of those hydrogens has access to 2 valence electrons because a bond contains 2 valence electrons. It is a position where an orbital from the carbon is overlapping with an orbital from the hydrogen. It makes a Venn diagram of glory. And in that overlapping space, there's an electron from each atom. So each of these hydrogens, through having a bond, has 2. Each of these hydrogens is set. Carbon, like most materials, follows the octet rule, wants 8 valence electrons. Each bond has 2, 2, 4, 6, 8. Carbon also has 8. We're set. We want to verify that because, well, if we don't have enough electrons, we're going to have to make double bonds. That hasn't happened here. So this is the finished Lewis structure for CH4. I'm going to do the one for O2. It is a diatomic. You probably have seen it before. However, I want to at least do one review slide where I do Lewis structures and go slow. Following this slide, I'll go fast. Gotta go fast. And I'm not gonna slow down after this slide. So if you need review for Lewis structures, now is the time to pay attention. So now we're gonna do O2. O2 has 2 oxygens. So we look up our boy oxygen. Breathe in. Oxygen is in column 6. Each oxygen will have 6 valence electrons. So that means the total budget that we have is 12. We'll do some mental math and speed up that budget tabulation a little bit. 12 VE. I'm taking my notes on oxygen in green. There's only 2 atoms, and when there's 2 atoms, there's no central atom. Both atoms are just attached to each other. Almost looks like glasses. We now are going to need to subtract for the bond that we just made. So we'll subtract from our budget. That drops us to 10. We then add electrons bouncing between the oxygens in pairs until either we have an octet on both or we've run out of budget. So let's do that. We're going to add in pairs, so we'll count by 2s. 2, 4, 6, 8. Who do we appreciate? 10. So we've hit 10. We're out of budget. We're out of spec. And what we see in the way that I've depicted this, the oxygen on the right has 6 electrons from lone pairs and 2 from the bond. The oxygen on the right has 8. The oxygen on the left, however, has 4 from the 2 pairs and 2 from the bond. That's 6. 6 is not enough. The oxygen on the left needs more. So the solution we were taught in the Lewis structure chapter was to maneuver electrons from the other oxygen into an additional bond. And that's why oxygen has that double bond when you see it depicted. And doing that, because you count sticks as 2 valence electrons, ensures that both of those oxygens have their full 8. All right, we'll start to speed things up a little bit. I will do my full due diligence on CO2 in a moment. Before we move on to CO2, though, I want to acknowledge the fact that we have 2 oxygens. So 2 moles of oxygen. You don't have to draw additional Lewis structures, although you may find it helpful when we get to the enthalpy portion of this problem, which requires a Lewis structure for every molecule, to draw a Lewis structure equal to the number of times that we have a stoichiometric coefficient. You don't need to, but many find it helpful. So because we have a 2 in front of O2, we'll draw the picture twice. All right, now we're going to do CO2. We're going to start off by getting the budget for CO2. We got carbon in column 4, 1. We got oxygen in column 6, 2 of those. So in tabulating that budget, 4 from carbon. We have 6 from oxygen. But we have 2 oxygens. Therefore, our total budget, 2 times 6 is 12, plus 4 is 16. Our budget for CO2 is 16 valence electrons. So in drawing this, we're going to draw carbon attached to oxygen. Oxygen is in the middle of those carbon is in the middle of those oxygens, because when we look at the periodic table, carbon is further left. Those 2 bonds each consume 2 electrons. There are 2 of them. 2 times 2 is 4. We have spent 4 electrons on those 2 bonds. That reduces our budget to 12. So now we have 12 electrons to add to the atoms, and the rule on drawing Lewis structures is the central atom gets last dibs. So as we count by 2s, we get to the point where each oxygen has 6 around it. 6 times 2 is 12. We have run out of budget. So carbon doesn't get anything. And when carbon is unhappy, it only has 4 valence electrons because it only has those bonds, and bonds only have 2 electrons in them. So between those 2 bonds, it has 4. When the central atom is unhappy, the molecule wouldn't form. However, it does actually form because we know CO2 exists. Scientists love talking about CO2. You're breathing it out right now. It exists. And the reason why it exists is because, well, when it forms, it does so with additional sharing from those oxygens. We are told to move additional electrons symmetrically until we have an octet around that central atom. And we have to do it twice for CO2 because CO2 had a carbon with 4. It needs 4 more. Each bond has 2 electrons, so we have to do it twice. And we're told to do it as evenly as possible. All right, so that's CO2. I know, isn't this a long problem? We haven't even done the new thing yet. That's so crazy. So we have our Lewis structure for CO2 now. We got one more. We have to draw the Lewis structure for H2O not once but twice. And this is the last Lewis structure that I'm going to do slowly. So we go to the periodic table. Oxygen still in column 6. Our lefty hydrogen is still in column 1. So our budget for this will be 2 times 1 for hydrogen plus 6 for oxygen. That is a total of 8. We have 8 valence electrons to work with. Hydrogen can't be the central atom, therefore we will attach hydrogen to it. Technically, because we've worked with this molecule a lot, we know that H2O has a bent structure. You don't need to get the geometry right to do these problems, however. I don't know, I'm a chemist. I'm going to draw it the way that I know it's shaped. All right. So we're then going to subtract the number of electrons that both of those have from the 8s to each. Subtract 4. That drops our total to 4. Because hydrogen is stable at 2, oxygen gets dibs on those 4. Even though it's the central atom. And doing that finishes our Lewis structure because oxygen has access to 2 bonds with 2 electrons each, and then 4 from lone pairs. Oxygen has 8. Oxygen's set. We are going to draw this Lewis structure twice, though, because there's a balanced 2 in front of H2O. Technically speaking, you don't need to do that. I believe the book chooses not to. I think visually, for the first-time students, doing this is helpful, although not strictly required. What we're going to do now is we are going to write a giant addition problem and use multiplication as a shortcut so we don't have a headache of adding too much information. We are going to add the energy associated with all of the bonds that are on the slide. We're going to add the energy for a hydrogen to carbon, a hydrogen to carbon, a hydrogen to carbon, a hydrogen to carbon. So we find that on the table. Got to look for it. It's right here. Carbon to hydrogen. The order those atoms are written in doesn't matter. And the reason for that is atoms and molecules are 3-dimensional, so they can rotate. So if this red ball is on the right or the left, it's just a matter of perspective, right? So those are it doesn't matter which one we do, left or right, or how it's notated in a table. Carbon is bonded to hydrogen. And in the structure, we have that 4 times. So we would take 411 plus 411 plus 411 plus 411. Hopefully you recognize that's annoying. So another way to do that same math is 4 times 411. And that's exactly what we'll write down. However, I want us to acknowledge that we are shortcutting addition, right? 411 plus 411 plus 411 plus 411. Because of that, we're going to use the addition subtraction rule for the whole problem, even though strictly speaking, there is multiplication in the equation I'm about to write down. Because we're shortcutting. Shortcutting addition. This is considered a giant addition problem. So we're going to write down 4 moles. Why is it 4 moles? Well, in the same reason we did hand math. This picture represents 1 mole of molecule. We have 602 septillion copies of it. That molecule has 4 bonds. It has 4 hands. So we have 4 times the number of moles of bonds. In the same way, if we had 100 of that molecule, we would have 400 bonds, right? Because, of course, the anatomy of this molecule has 4 hands. It has 4 of this bonds. So it's 4 times the number of moles of bonds. It's not a crazy idea. Just like a car tends to have 4 tires. There's a difference between counting units and parts on a unit. So that's what we're doing here. So we're going to multiply 411 kilojoules per mole by 4 moles. And that 4 came from counting these bonds. There's 4 of them. This is why the table is presented in terms of per mole. It allows us to factor in the fact that there's multiple bonds. And by the time we are done, all of these per mole units are going to cancel. So our final answer has no moles in it. It's going to be the total energy with running the reaction once. All right. We're now going to look at the energy that is associated with the other reactant, which is O2. We drew this twice. There are 2 copies of it. We have this bond twice. We have, this is considered to be 1 mole. This is considered to be 1 mole. So how many moles of that oxygen, the oxygen double bond, do we have? Well, we have it twice because there's a balance coefficient. So we have 2 moles of it. So therefore, we're going to add the energy associated with that oxygen, which is 494. And we're going to multiply that by 2 moles because there's 2 copies of it drawn. And what will eventually happen is that these moles will cancel and we'll be left with a measurement in an energy unit. What I want us to notice is that that accounts for all of the reactants, doesn't it? We have all of the reactants here. And the equation that we're given that lets us calculate delta H tells us to sum all of the energy in the reactants. So these are the reactant energies right here. This is the energy to break the reactant bonds. Ultimately, we are going to also get the energy required that is released from the product bonds. And that, where we need to write those notes, is where my face is. So I need to go over here. And we'll do that. We're going to do another calculation that is add all of the energies of the products. So let's do that. We're going to look at the products now. We have this CO2 right here. That picture represents 1 mole of CO2. However, that 1 mole of CO2 has 2 bonds. We would say that we have 2 moles of bond. So we're going to multiply by 2 moles. And we look up that bond. So it is oxygen double bonded to carbon. We find that in the table that is above me. And we make myself really small so we can find it. Oxygen double bonded to carbon looks like it's 799 on the table. And eventually, the moles will cancel. All right, then we're going to add the energy from the other products, which are the 2 water molecules that we drew. Each picture we drew represents 1 mole of water. Within each picture we drew, each bond represents 1 mole of bond. So therefore, we have 2 moles of bond within each picture. Or just count the sticks. How many sticks of hydrogen connected to oxygen are across those 2 pictures? 4. So our total number of hydrogen to oxygen bonds is 4 moles. And then we're going to look up the energy value for that on this table. Carbon connected to hydrogen to oxygen. No, not carbon. Hydrogen connected to oxygen, if we find it on the table, is 459. And eventually, when we carry this math out, the moles is going to cancel. When you do any of these problems on the test and give me answers, I should not see per mole on your final energy solution for our delta H's. This is the energy that is released when the bonds form. We will get both of those answers and we will subtract them. A note on something I already said, but I want to emphasize it. So if you're like, stop repeating yourself, sometimes I need to emphasize things. This is a giant addition and subtraction problem. It is technically 411 plus 411 plus 411 plus 411 plus 494 plus 494 minus, in brackets, 799 plus 7999 plus 459 plus 459 plus 459 plus 459. I hope you recognize typing that into your calculator is obnoxious. And we're using multiplication, so we don't have to type that into our calculator as a functional shortcut. All this to say, don't round till the end. We are going to round our answer to the lowest level of precision that all of our energies that we wrote down have. They're all to the ones place. Therefore, we're going to write our answer also down to the ones place. We have an addition problem in brackets. We have another addition problem in brackets. We then subtract the two answers. If you want to show work between those two, have at it. I'm going to. So, let's do that. Let's do the first one in brackets. Clear it. Get out of scientific notation, because I think that would just be confusing. We have 4 times 411 plus 2 times 494. So the energy associated with the reactants is 2,632. We'll write that down. I'm trying to figure out what color we should do it in. I've used too many colors. I'm like, I want to use a unique color. I've been told that red is hard to read, so I'm not going to use red. 2,632. And now it's just kilojoules because the moles have canceled out. That subtraction sign will drop down. We are then going to get the answer in the other set of brackets, and then we know what two numbers to subtract. This is the part of taking the difference for a delta H. So 2 times 799 plus 4 times 459, if we can type it in accurately. And that comes out to 3,434. So this difference is the change in enthalpy. So we just got a little subtraction problem, and we've already confirmed, yeah, it's going to be to the ones place when we write it down. And that will be the net amount of energy in the reaction. So let's do that. Little subtraction-do. 2,632 minus 3,434. Negative 802. It is to the ones place. That sign does matter. The problem doesn't tell us to interpret the sign, so we don't have to. However, negative signs are exothermic. No duh. We're working with the combustion of methane. I hope it's hot. Otherwise, we did something wrong. So that would be the final answer here. No, this is not the only problem that we're going to do. Things have heated up a little bit, but I need to take off my sunglasses. I hope chat is feeling okay. Sterling's mad. He's like, why are you doing this to me? You've ruined my life. They are. Hopefully we're feeling okay. We're going to do another one. That's a really long problem because I was thorough. Because I reviewed how to draw Lewis structures and did 4 Lewis structure problems, right? I could not make it the entire class. It was hurting my eyes. I'm in dark mode. It was bad. I'm sorry. folks asking me to repent. All right. So if we're feeling good, we're going to do a long problem. Isn't that great? We're going to do a problem that is a reaction that you probably have studied before. Does anyone recognize this formula? C6H12O6. Or maybe more holistically, does anyone recognize the entire reaction? CO2 plus H2O produces, as Lydia and Jerusalem got it correct, glucose and O2. What reaction biologically makes sugar, and releases O2? You may have heard of this reaction before. You are benefiting from it right now. This is the chemical representation of photosynthesis. Plants take CO2, combine it with H2O and sunlight energy, and they output sugar and O2 as a result, which means it's an endothermic reaction, although we don't know what its value is. So we're going to actually use this slide to figure out what its value is. I have already drawn the Lewis structures for CO2, O2, and H2O. So I'm just going to magic them onto the slide because we don't need to waste our time with those because we've already done them. So I'm going to redraw all of them for us. Additionally, the number of copies that we have for each of these molecules is quite high. I don't want to draw CO2 6 times. So what I'm going to do instead is I'm just going to write a little note that says, yo, we have 6 copies of this. Technically speaking, we don't need the dots to count the bonds. You do correctly need to note if it is a double bond or a single bond. However, I'm drawing the dots because I'm a completionist. So we have 6 of those. We also have 6 H2Os. We'll draw a nice big bond so you can read them. So these are our reactants. And then we have the O2 left to draw. And O2 looks like this. We also have 6 of these. All right, so we will start off by writing down notes on the number of bonds that we have in CO2. So each of these bonds represents 1 mole of bond, which means we have a total of 2 moles of bond in 1 mole of CO2. We have 6 copies, though. So therefore, once we account for that times 6, we have 12 moles of bond. And you could draw that molecule 6 times and then count 2 per, if that helps you. So the total number that we have is 12 moles. 2 per instance of CO2. We have 6 instances. 6 times 2 is 12. So we have 12 moles of oxygen double bonded to carbon. We look up oxygen double bonded to carbon on the table. That energy is 799. We're then going to add the energy for the other reactants. Same thing. We have hydrogen single bonded to oxygen twice. We have 6 copies of that molecule, though. 6 times 2 is 12. So we have 12 moles of that bond. So let's calculate that. Oxygen single bonded to hydrogen is 459. And we'll have to write that per mole. Oops. That probably sounded awful. I apologize. This is the easy part. We have all of the energy associated with the reactants now. So that is the energy required to break the bonds. Great. Now we have to do the products, which is a nightmare. Let's do it. I'm mentally like, how do I want to format this? I'm still wondering how I want to format it because, as you notice, glucose is quite big. You're not expected to draw the Lewis structure for glucose. If you had to do a structure this large, I would give it to you. I have given it to you. So we're going to do that. The goal is just to subtract the energy from these two piles of molecules. So we have 1 mole of that double bond between oxygen attached to double bond to oxygen, except we have it 6 times. 6 times 1 is 6. So we have 6 mole of that double bond, and we can look it up in the table. Its energy is 494. We're then going to add the energy from that thing on the right. However, it's awful. We need a whole table. We need to do like a whole massive side calculation in order to get the energy in a molecule this big. So let's just identify which bonds we have. We'll work through them one at a time. The bonds, you can pick arbitrarily which one we start with. The one I'm going to start with that we have 1 of is carbon double bonded to oxygen. So we're going to do a little side calculation down here. We have, I'll color code it. We don't need to write out the bond identity. Carbon double bonded to oxygen, if we look for it, is 799. So we have that bond 1 time. So we're going to multiply 799 kilojoules per mole by the number of times it appears in the structure, which is once. We're then going to pick the next one that we want to work with. It doesn't matter what you pick, but you need to pick something because we need to identify all of them. I'm going to do hydrogen bonded to carbon next. And I'm just going to circle them to help me count. We're specifically looking for a stick between a C and an H. We want to make sure we don't miss any. And as you go through the picture, the number of circles that I just drew was 1, 2, 3, 4, 5, 6, 7 of those. So we have 7 moles of that bond. We now find carbon to hydrogen on this table. It's 411. We're now going to do the next bond. Let's do hydrogen bonded to oxygen next. All right, the number of times I circled that was 1, 2, 3, 4, 5. 5 times. And now we'll find that on the table. Hydrogen bonded to oxygen has an energy of 459. There's 2 more. They're hidden because the picture is messy, but there are 2 more. We have carbon bonded to oxygen with a single bond. And I have circled all of them. Now we can just count those. 1, 2, 3, 4, 5. We want to look up the energy for that on the table. Carbon single bonded to oxygen is 358. And then we have 1 more. This one is the most subtle of the entire set because it's in the middle of the molecule. Scientists call this the backbone of the molecule because it's the structure off of which everything else branches off of. We have these carbons in the center that are attached to each other. And the goal is to count the sticks, not the atoms. So we have this carbon-to-carbon connection. We have the adjacent carbon-to-carbon connection. Yes, these 2 connections share a carbon. You're counting the sticks, not the atoms. So that's 2. Here's the third one. Fourth one. Fifth one. So there's 5 of those. Carbon single bonded to carbon on the table is noted as 346. And we're going to add all of these together. And then ultimately we have the energy of the products. Oof, that was a lot. So we have this giant addition problem here. And then we have the one to the left. Let's do the one on the left first because the other one scares me. It's spooky. Let's do this one first and drop down an answer for it. So we have 12 times 799 plus 12 times 459. This is the total energy associated with the reactants. Keeping it to the same precision as the other numbers, that's the ones place. The total energy associated with the reactants is 15,096 kilojoules. That's a lot of energy. There's a lot of energy stored in many copies of CO2 and water. All right, now we're going to get the answer for this giant pile of multiplication and addition that is accounting for the products side. So we'll start off with the 6 times 6, 494, that came from the 6 copies of the water. 6 times 494 plus, and then we're just going to add all of these little bits. 1 times 799, I'm just going to type plus 799. Plus 7 times 411. Plus 5 times 459. Plus the work in this light blue. 5 times 358. Plus the work in this dark blue. 5 times 346. We've typed it all in. It was a lot of small number times big number all added together. When you type that in, you get 12,455. Subtracting these two, because the goal is to add all the energies associated with the reactants, add all the energies associated with the products, get those answers. We have done that. Subtract the 2 answers. That is the total energy. That is the change in enthalpy. So let's get that difference. 15,096 minus 12,455. Keeping it to the same precision as all the numbers, which is the ones place. We're going to write down 2,641. And that's positive. A positive change in enthalpy tells us that we have an endothermic reaction. Oh my goodness, our plant doing photosynthesis is going to absorb energy. Where does that energy come from? It comes from sunlight. All right, we'll look over in chat. A bit of a longer problem. I'm in chat right now. None of this is associated with the problem we just did. Peter says, is this going to be on the test? I am spending time on it. You should be prepared to do a problem that is this hard or easier. Penny says that she's confused and doesn't know when to subtract. This problem is messier than the last one. We're looking at our core equation up above. You want to take all of the energy that is in the bonds and add all of the you want to take all the energy in the reactants in those bonds and add them all together. So all the bonds that are in CH4, all the bonds that are in these O2s. You then separately want to take all the energies in the products, all of the energies that are in the bonds of CO2, all of the energies that are in the bonds of H2O, add them together. Thus, you'll have the total energy in the reactants, the total energy in the products. That's the work down here. This is reactant energy. This is product energy. You then take the difference. So you subtract the difference between reactants and products. That's where the subtraction ultimately is going to pop in. What happened to the 12 moles of the H2O? Did I forget it? I don't think I did. Right here. 12 moles of CO2, 12 moles of H2O. We'll double check if I missed it. It's possible I missed it, Wyatt. As we see, there is a lot going on in these problems. Nope, it got accounted for. It's in this number. 12 times 799 plus 12 times 459. This is the energy from the H2Os. Incorporates to this total reactant energy. Penny says, so it's always reactant minus product. It is reactant minus product only for bond energies. This is the only time where we have it in that ordering. And it has to do with the fact that we're comparing breaking energy and releasing energy, and those are fundamentally different, and when the equation gets derived, it gets really weird. What is the sideways M for? That is a mathematical symbol, sigma. No one in here is being called a sigma. This is a math symbol. It is a Greek letter. It tells you to add stuff together. It means take the sum of. Not that you're low-key cool. Right. Anyone else? Sigma is a Greek letter that means add numbers. So this equation says add all of the energies for the reactants. Add all the energies for the products. Subtract the 2. All right, anyone else? Hopefully we're feeling okay. We started at 10 a.m. Eastern. It is now 11:12 Eastern. We have like 15 more minutes to learn another type of problem. The good news is the problem that we're going to end on is a lot easier than this one. All right, if chat is feeling good, I need to dance over here. A bit of a note. This slide says that we're going to be working with Hess's law. Hess's law states that the enthalpy of a reaction is a state function. A state function generically doesn't care about how we got to our end position. There are other state functions that exist. If you have taken physics before, you know that displacement is a state function. Displacement is your distance relative to an origin. So if I were to drive in donuts in a parking lot, just go in circles for a really, 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 really long time, the number on my speedometer is going to keep ticking up, right? The distance that I'm covering with my car is going up. I'm burning fuel. I'm burning rubber. I'm having a fun time. However, if I were to then apply my brakes and put the car in park, the distance from where the car started when I first started doing donuts is almost nothing, right? The path that I took to that position, if I were to draw a straight line from where I started on that circle to where I ended on that circle, is a pretty small number. That's a state function. It doesn't care how I got there. I could have gotten there very inefficiently. I could have driven in the circle 20 times, a million times. That number would end up being the same if I stop in the same position each time. Making products is also a state function, which is very, very, very important, because this tells us that if we start out with carbon and oxygen and we go directly to producing CO2 with those, Or if we were to react via another pathway and we have this intermediate step where we make carbon monoxide and O2 and then use those to make CO2, the total amount of energy that is needed will be the same. It doesn't matter if we go straight to the final destination or if we make a pit stop. If we go through more inefficient version of the reaction, the energy needed for the sub-step plus the energy from the sub-step to the final destination will be the same as going straight to the final destination. This slide exists because it gives us permission to use this table. This table will also be given to you on the test. You will not need to memorize it. Also, I noticed that the equation that is displayed on the PowerPoint has decided to not look right. So let's see if I can iron that out. There we go. It just got bumped. Now it's actually legible. That's nice. We like being able to read our slides. So what this table says is that because of Hess's law, we can determine the energy that is needed to make a specific chemical in isolation. The amount of energy to make CO2 will be the same every single time. It doesn't matter what makes it or what pathway was needed to make it. The energy associated with CO2 and its bonding is always the same. Because of that, we can look at a table like this and go, oh, the energy needed to make CO2 is the same every time. To make 1 mole of CO2, it's always 394 kilojoules. And what's nice about this, then, is if we are given an entire reaction with all of its named reactants and products, if all of the named reactants and products are on this table of formation, we don't have to do the long bonds method that we just spent 75 minutes on. I think we can appreciate the fact that drawing all those bonds and Lewis structures was kind of a pain. I don't know if anyone enjoyed doing that. It was a lot to track. It was a lot of numbers to consider and a lot of places to make mistakes. So we luckily have this alternate method, but it is restricted by a couple of things. One, if chemicals that are in the problem are not on this table, we can't use this method that is faster. If you don't have an energy for a chemical, you can't use this method. Two, the experiment needs to be done under what's called standard conditions. These numbers change based on the temperature and pressure of the room that the experiment is done in. If the room is not at 25 Celsius or 1 atmosphere, you can't use this table to do the problem. That is what the degree sign means. When you see a degree sign attached to a variable, that is a way of communicating these are measurements at standard conditions. It feels like an arbitrary extra symbol, but it specifies these are observed under standard conditions. And then the last thing, if the problem has a homonuclear diatomic, you remember, hopefully, that list of broccoli molecules, such as O2, N2, F2. Those are all substances that naturally occur and form easily on Earth. We consider the energy that is needed to make them 0 because they're prevalent. So when we do problems with O2, F2, N2, etc., look at the whole table. We're going to use values of 0 for their enthalpies when doing the calculation. So what I want you to notice here is that the subtraction is flipped. We're now doing products minus reactants. How do you not mess that up? Well, you write both methods down on your crib sheets as they appear in the textbook, and when you're doing different types of problems, you make sure you're using the correct equation. So if we're not using bond energies and we're instead just referencing this table, products first, reactants second, add all the energies with the products, add all the energies with the reactants, subtract the two answers. And we'll do the same type of rounding. We're just going to round to precision at the end. So with that, we're going to practice. We do want to make sure that our reaction is balanced before we start the problem. A quick glance at this reaction shows us that it is balanced. So we don't need to do extra work here. 1 sulfur on each side. 4 oxygens on each side. 3 plus 1, 4. and 2 hydrogens on each side, so no balancing needs to be done here. Our equation for a change in enthalpy of formation, let me make sure I get the symbols right, is equal to all of the product enthalpies added together off of this table, and then all of the reactants enthalpies off the table added together, and then subtract those two. So we're going to fill that in. Again, the degree sign just says this is at standard conditions. It is a chemistry symbol that says we're at 25 Celsius and we are at 1 atmosphere. So let's start to chart this out. Our change in enthalpy is equal to, let's look at the products. The only product we have is this. If we look for it on the table, it is negative 814. The balanced coefficient in front of it is a 1. So it's 1 mole times negative 814. The unit on this comes out of the header of the table. It's kilojoules per mole. And that is all of the product energies. We're now going to do the reactant energies, because we do products minus reactants for these formation problems. Let's move to that. The reactants, we're here, are SO3 and H2O. So we have 1 mole of SO3. We got to find SO3 on the table. It's negative 396. The unit on that is kilojoules per mole. We're then going to add, because we're doing sum of all of the energies of the reactants, the 1 mole of H2O that we have. We got to find H2O on the table. Caution, you have to pay attention to the phase. This problem specifies that it is a liquid. The table has enthalpies for both liquid and gas. You have to write down the matching one or your answer will be slightly off. So the liquid version of water is negative 286. All right, so we have 2 little addition problems that are going to, when we simplify this down, give us both the product and the reactant energy respectively in that order. Again, products first, reactants second, for this new type of problem. So let's simplify and clean that up. We'll do the products first. 1 times negative 814 is negative 814. However, we did put that 1 in so that the moles goes away. That's actually pretty important. So we end up with negative 814 kilojoules. We now have a little addition problem. The point of that 1 mole is, again, to make the moles go away. So that we have a final answer that is in kilojoules. So we have effectively negative 396 plus negative 286. We'll do that. Comes out to negative 682. To just separate a subtraction sign from a negative sign, I find it useful to put that in parentheses, just for your own clarity. So our problem is basically done now. See how much faster these are? We prefer to use this table when possible. So negative 814 on our calculator. Minus negative 682. As long as we've typed our signs incorrectly, that comes out to negative 132, keeping this answer to the ones place. And the unit on that is kilojoules. The problem didn't ask us to solve for this, but it is negative. This is exothermic. So this reaction would be hot. All right, we're going to check chat. If you have questions, you should put them in chat. We'll do one more in a second. Wyatt says, so put this table on our crib sheet so we don't have to do Lewis structures. This table will be given to you on the test. Now, this method is better. It's better because it's faster. However, it has limitations. If the reaction is not at standard conditions, using this table is illegal. It will give you wrong answers. Secondarily, sometimes reactions don't have substances that are on the table. And if that happens, you can't use this method. You would have to use the bond energy method. And if that happened, yeah, if this method is ineligible, either because we are not at standard conditions, which is 25 Celsius in 1 atmosphere, or the problem doesn't use that degree sign, which also communicates you're at standard conditions, you have to use the other longer method, the bond energy method. Now, I do have time for one more, so I want to do that. There is a small wrinkle in this problem in the fact that it gave us a diatomic. Now, remember, diatomics have energies of formation, enthalpies of formation of 0. Water's just there. Not water. O2 is just there. It's fine. We just use a value of 0 when we do the math. It's not even worth our time to put it into the math because adding 0 3 times is a waste of time. So we're just going to go straight to the problem. We're again going to use our equation for enthalpy of formation. What gives us that permission is this degree sign in the question, which implies we're at standard conditions, so we're allowed to do this. So again, we sum all of the enthalpies of the products. I'm going to write it in caps to emphasize which comes first. We're then going to add all of the enthalpies off of the table for the reactants. We subtract the 2. Okay. So we got 2 little addition problems that then get subtracted. So we'll start out with the products. Let's start to take notes. I'm trying to color code products and reactants a little bit for you as we do these to help you follow along more clearly. So we start off with the CO2. We have 2 moles of CO2 because there's a balanced coefficient in front of it. And the reason why this matters is the table gives us the energy for 1 mole. We have 2 moles. And the table says that's negative 394. We're then going to add the energy for 4 moles of water. There's a balanced 4. You should always check these problems to see if they're balanced. This one was just given to us pre-balanced. When we write down water's energy, make sure we're careful of the phase that it is communicated in. It's a gas, so this time we want the negative 242. Asher says, why is 3O2 equal to 0? Because of a subtle line that I noted on this slide. Homonuclear diatomics have formation energies of 0. It was there. It's an important flag to put in your notes. And if you don't remember your diatomics, go back to that broccoli slide that I showed you in previous lectures. All right, so those are the products. We're then going to subtract the energy for the reactants. Again, because O2 is a diatomic, we consider its enthalpy to be 0. Okay. So we're only going to consider that ethanol then, which is CH3OH. The table lists it as negative 239. We have 2 copies of it, so that's 2 moles. So we have negative 239 kilojoules per mole 2 times. Now, there's a world in which you could do like straight calculator entry on all of these and just get the answer on your calculator. I find, to not confuse folks, that I like to write it down in 2 steps. So we're going to get the answer for the sum of the math in green, which is the products, And then we'll get the answer for the sum of the math in orange, which is the reactants. We'll then take the difference and class will be over. This is the last problem we're doing. I'll, of course, save time for questions. So 2 times negative 394. That comes out to negative 788 plus 4 times negative 242. So the total energy for the products is negative 1,756. Moles will always cancel out when we're doing these. We're then going to do the reactants in orange. 2 times negative 239. That comes out to negative 478. When I subtract a negative number, I like to put the negative number in parentheses just to kind of quarantine that negative sign so I don't lose track of it. That isn't mandatory. I think parentheses just like help make your work not blur together. So they do have that nice use to them. So we have our two numbers that we're subtracting from each other. We'll do this. We want to make sure that we get signs and operators correct. Don't let negative and subtraction signs blur together. That can be messy. So we have negative 1,756. We are subtracting negative 478. We hit equals. That comes out to negative 1,278. The problem did not tell us to interpret the sign, so this is more than sufficient for full points. However, for extra emphasis, negative changes in enthalpy are exothermic reactions, which of course, we are reacting ethanol with O2 and it is making CO2 and H2O. That is combustion. Lighting ethanol on fire is hot. That's not crazy. Actually, that's not ethanol, that's methanol. But still, writing methanol, wood alcohol on fire, is hot. So that's not that surprising of a result. We now just have the quantity of that energy, however. All right, we're going to double check chat. If you have questions, you can also slam those in the chat box. And if I miss a question, you should type it again. I'm not ignoring you. I just missed it, and it was not on purpose. I'm just scrolling through chat, making sure we're okay. Chat's gassing me up a little bit. Appreciate you, fam. All right. So if we're feeling good, this is going to be where we end. Reminder, you can reach out to me outside of class also. We'll be returning next week to wrap up the second half of this module, and we should have time for extra practice this chapter. It doesn't get too crazy. All right, everyone, make sure that you stay curious. I'll see you next week. Have a fantastic rest of your week, and I hope that your week is starting off to a really good start. See you later.